Hi. So welcome back to the lecture series on points of topology. I welcome you all to the next lecture. In the last lecture we have started with the definition of metric spaces and also gave some examples of metric space, some beautiful example of metric, not matrix, it's a metric. And just a short introduction of non-linear spaces. We'll come back to the nonlinear space again once we will study the Banach spaces and the completeness properties, but for now let's keep it. So I believe that you have gone through all the concepts that we introduced in the last lecture and managed to see these books. If any one of you is highly motivated and interested to solve the problems, just problem practices, you can I refer to this one, that is Kumaresian Topology of Matrix Spaces and Monkesh as well. So these two books are very beautiful and useful for problem practice and concept building. Okay, so let's move ahead. So today our topic is, not a topic. So our motivation is to study what are the topological properties of metric spaces. Though I will define topology in a most formal and rigorous way in a couple of lectures, but still let me just give some basic motivation that why should we need to study the topology. Okay, all right. So suppose let us consider an open set 0, 1 is subset of R, right? So what are the properties then one can think of about this real lines? First of all, the picture represents the following, that if this is a real line, for instance let us consider, so it is 0 and this is 1. So what is actually it is meaning? This is actually meaning that I am considering all the elements in between, strictly in between 0 and 1. So that means first you consider just you put a stick along this and cut the terminal points. Okay, so that means it is basically you can think of it is a line without or any particular space without any boundary, where the boundaries is removed. Okay, so the same intuition we can construct in arbitrary topological spaces. So first the notion, so the analogous notion in arbitrary topological space is something called open ball. So what is an open ball? Suppose X comma D is a metric space and let us consider small x not belongs to capital X and delta is strictly larger than 0 and delta belongs to real number. So then we consider an open ball of the following way. So it is B delta x naught. This is set of all small I belongs to real number such that d of x naught comma y is strictly less than delta. Okay, so that means if you have a metric like this, first you consider a particular point small x naught and take a certain around any point, let's say it is any point P which is at distance delta from x naught, and traverse the point with around x naught, keeping this particular delta fixed. So that means you are just traversing in this way. Okay, then you can see that it covering some area in between x. Let us take this x, and it is covering some area, right? So this is my area. It is covering by the traversing point. So the trajectory is basically covering this particular area marked with green zone. Yeah. All right. So then what you are doing, you are just removing all the entire boundary. So this is what is actually explicitly getting identified with this notion. Okay, so that is called an open ball. So in R, an open ball is nothing but any open interval, that is x naught minus delta and x naught plus delta, that we have just seen here. So what is this? Just take the midpoint of 0 and 1, that is half. So 0 comma 1 is nothing but b half half. Okay. So that means every open interval is basically an open ball. Okay. Now similarly in R2, suppose we have R2. So what are the in case of R2, what is the most common choice? So suppose we have let's say R2 with usual norm. Okay, that is it's a Euclidean topology, Euclidean metric space, Euclidean metric space. So then the what will be the structure of the open ball? So open ball will be the following, that suppose we have B delta. So in case of R2, it should be x naught comma y naught equal to set of all x1 comma y1 belongs to R2, such that norm of x naught comma y naught minus x1 comma y1 is strictly less than delta. So that means what is this simplifying? So this is basically simplifying that square root of x naught minus x1 squared plus y naught minus y1 square is strictly less than delta. So that means x naught minus x1 square plus y naught minus y1 square is strictly less than delta square. Okay, so that means you are first you're taking, let's say it is my x naught comma y naught, and around certain delta. This is my open ball. Let's say so it is my open ball, and let us basically we are taking, just make it fill up. And remove the ball, just remove the boundary. So this is my delta. Okay. Similarly, if we consider, so it is basically, this is said to be an open disk. Okay. Now again, suppose we consider R2 with respect to 2 norm. Okay, they say this is or metric induced by 2 norm. So then just instead of this, it will be just getting replaced with x0 minus x1 plus y0 minus y1 is less than delta. So that means it is basically of this form. So x0 minus x1 and x0 minus. Okay, so for instance, we can consider x0 to be x0 comma y0 to be a 0 comma 0. Then it will be easy for us to visualize. So if it is x0 comma y0 is 0 comma 0, then of course it will be modulus. Yes. So then it will be nothing but mod of x1 plus mod of y1 is less than delta. That means first it will be like this. So this one, this one, so this is my delta comma 0, it is minus delta comma 0, it is 0 comma delta, it is 0 comma minus delta. So the inner portion only. In fact, if it is on x0 comma y0, then you have to take first mod of x0 comma y0 is equal to delta. So first let's see, it is my x0, so it is my x0 comma y0. This portion only. Okay, and let me just give you a exercise. Verify what will be open ball, of course pictorially, in R comma max non. So let me give the name. It is said to be pin square. We'll find that it is a square where all the boundaries are getting omitted. Alright, now suppose X command is a metric space and U is subset of X. Okay, of course it is non-empty. Then U is said to be open set if there exists, if for every small x belongs to U, there exists delta belongs to the real number strictly larger than 0, such that d delta x is inside U. That means Suppose if it is my topological space X, and let us consider this a matrix space. I mean, there's a set U. So what is actually this actually getting implies that I can cover the entire set with an open ball like this. So whatever element I will choose, I must get a certain real number such that the ball with that certain radius and center at that particular point be chosen is completely inside U. So that means U can be covered up with all such small open balls. Okay. So then we say that. So that means basically this will imply that U is basically union of all such small x belongs to U. Of course, this delta should be depend on small x belongs to U B x of delta x. Okay. So then we say that U is open, and once the complement of U, this is open. If we have any subset of a topological space of a matrix space capital X, then if the complement of that matrix of U is open, that will imply that U is closed. Of course, in matrix space there is also another analogous definition of closed set, that is via limit points will be defined, but this particular definition of closed set are going to be helpful for us to study topological property, in general topology. Okay. So meanwhile you can already check these things, that first of all, suppose X comma D is a matrix space. Then first of all, X and empty set both are open. Secondly, open sets are closed under arbitrary union. And secondly, are closed under finite intersection. So one can easily check it, because if you take any capital X, then of course and I mean just by definition of the open ball, every element will be inside capital X. So you can take any element and any arbitrary positive real number, just apply this P delta X, you find that, oh I'm sorry, I should write it here, this should be capital X, the element should be from capital X. So the elements should belongs to from capital X. So of course this is subset of capital X. There is nothing to do anyway. And by vacuous condition, phi is already open. By vacuous statement. For arbitrary union, you can take any arbitrary collection of open sets like let's say uy, I'm sorry, so uy small I belongs to capital I, where I is any arbitrary set. Then union of small I belongs to capital I, once you consider this and take any point small I belongs to capital Uy, x must belongs to some Uy1, right? Where I1 belongs to capital I. So then you consider B, and Uy1 is itself open, so you can have a particular B delta x such that the open ball centered at small x and with radius delta x is completely inside Uy1. So this is inside entire small I belongs to capital I, this entire union. So that means union of small I belongs to capital I, this entire union, this is open set. As well as if we consider any final intersection, so small x belongs to, let's say, small j belongs to capital J, or let's say j equals 1 to n uj. So for every small j I should get some delta x that will depend on as well as j, then such that, I mean not x, let us take delta j. Delta j that will also depend on x such that b delta x is inside uj. Then what I will do, so I will take the minimum of all the delta j, so delta equals to minimum of all delta j. And why delta j minimum can be chosen? Because there are finitely many delta j's. Okay, so then b delta x will be inside b delta j of x for every j, and that will be inside uj for every j. So that means b delta x is inside intersection of all uj. Let's say 1 to n. So it is closed under finite intersection. So just remember these properties. Okay. Now, what about the, now you see that once we try to introduce the concept of open set, we say that we are removing the boundary. So what we actually want to mean by the boundary? So there's a definition of boundary is the following, that so boundary means suppose x comma d is a metric space, then let's say x a is subset of x, then boundary of a y. What is the boundary? So boundary means from the entire a you remove the interior of it. So interior of a means set of all interior points of a. So interior, I mean by interior point means that there exist for, I mean, so let's say small x belongs to capital A, then x is said to be interior point if there exists some delta belongs to real number strictly larger than 0, such that b delta of x is inside it. So just whenever any element will satisfy this particular property, then is the interior point. And of course, once you have any open set, then boundary of a, this is phi, then a minus, because a in that time a is interior of a itself. Okay, all right. Then there is something called limit points. So as a limit point, suppose we have any A subset of X. Let us take small x belongs to capital X be any element such that for any delta belongs to real number which is larger than 0, B delta X minus singleton X, you take that B delta X and then remove small x just, and that will intersect with. So that means in capital A there is also one element in which is different from small x and as well as in B delta X. That means the preparation is following, that suppose you take any element on the boundary of this set, then whatever element you choose, that it will cover this particular region, right? Whatever delta you choose, it will cover certain element, certain amount of this set, right? So then each of the boundary elements are limit point as well. But every time it is not necessary that the elements, boundary elements, boundary points will be. Those should be at the boundary one as well. So yeah, okay. So that's the limit point of a. It is limit point of a set, not limit point. We are comfortable with, or familiar with something called limit point of a sequence, but it's limit point of a set. In fact, in sequence as well, the motivation is the same. Like suppose we have a sequence, let's say 1 by n is tending to 0. So that means if you have it 0 here and 1 here, here 1 by 2, 1 by 3, and so on. So that means whatever, and just remember the definition of a convergence sequence, like there for any epsilon belongs to real number, there exists capital N belongs to natural number such that xn means here it is 1 by n is less than epsilon. So that means basically whatever the surrounding or neighborhood you choose around 0, it will intersect with all these set 1 by n in your natural number. It will intersect with this set, some eliminate from there. And of course 0 is not there. Anyway, 1 by n could, this set doesn't contain 0. So this particular property is significant, like this removing criteria is significance once small x is contained in capital, otherwise no. So otherwise this has no any significance, but if small x is in capital A, then it has a significance that you are omitting small x, and then there is no question to get small x again in intersection. Alright, so we have defined the limit points and as well as some boundary points. By the way, can you tell me one thing, that we have defined something called interior of a set, right? So suppose O be in another open set such that O is inside A. A need not be open, okay? But in A we have, inside A we have another open set which is contained in capital A. So then can you tell me one thing, that what is the relation between interior of A and O, means which inclusion we will take, this one or this one? So of course you are get familiar, it must take capital O, because once it is a open set, it must consisted of interior points in capital A, and interior of A is a set of all interior points. So of course this inclusion will happen. So that means interior of A is such an open set in capital A that contains any other open set sitting inside it. So you can say that interior of A is the largest. In fact, interior of A is also as an open set. Is the largest open set contained in the set capital. Okay. Now, suppose you have, let's say, 0, 1 and singleton 2. So what are the limit points of this set? You see that only 0 and 1 are two elements which can satisfy the property of getting limit points. So that's why 0 and 1, this is a set of a limit points. So the limit set of a limit points this collection of all the limit points is defined to be as derived set of A. And it is denoted as dA. Okay. Now, suppose A is subset of capital X, and of course X is a metric space. Every time I may not be able to say that X comma D is a metric space, but once I will say X, you have to think that it is a metric space. So let's consider X is a metric space and A is subset of capital X. Of course it is non-empty. Then let A is placed to the property that A contains all of its limit points. So then what can you say about the criteria of A? Is a open set, closed set, or whatever. So of course then A is closed set. Why is closed set? So to prove it is closed set, we have to define the, just show that the complement of A is open set. So let small x belongs to a complement. So as small x belongs to a complement, so for sure small x is not limit point. So as small x is not limit point of A, so their x is delta belongs to real number, comma delta larger than 0, such that B delta x inside capital A, this is completely phi. We have already said that x is in A complement, so x is neither a limit point, and of course x doesn't belongs to A. So that means B delta x is completely inside phi. That means B delta x is inside a complement. So A complement is open set. So we have got a proposition that A subset of X is closed if and only if A contains all of its limit points. No, all of the limit points. So that means once you have any closed set, it must contain the limit points, and all the boundary points are limit points. So that means closed set must be boundary. It's important property. Now let A is subset of X. Then we can define the derived set of A. That means this contains all the limit points of and then A union of derived set of A defined to be as a closure. It is closure of A. So that means from any A you can quickly cook up with a closed set. And what is the property of closed set? You see that this is union of the entire set and with derived set. So of course A is inside A closure. So here the statement is closed set containing capital. Okay. So now you can easily check that A closure is closed. Now to prove it is open, so closed, we need to just take that A closure is equal to A complement union derived set of A complement. I'm sorry. A closure means A union the derived set of A. So A closure complement means A complement intersection derived set of A whole complement. So if you take any element, let's say small x belongs to A closure complement, it belongs to A complement as well as D of A complement. So that means there exists some delta belongs to real number such that B delta x is inside A complement. And if you have any element, let's say small y belongs to B delta x such that small I belongs to D of A complement, then let's say D of A, then this will imply that there exists some B delta y of y inside A. Now then choosing a suitable delta 1 which is equal to just suppose here is my x, this is my A, and certain element is B closure. So I take some small b which is quickly inside this. So from what we can see that it is inside small I belongs to A. So this is a contradiction. So B delta x will be complete. So y must be inside A complement. So that means derived set of A complement. So B delta x subset of A complement as well as the complementary derived set. That means and hence a closure is closed set. So the definition that I promised you to give in terms of limit points is the following. Once a set contains all of its limit points, is said to be closed set. So as an example, most common example is closed in any closed interval 0 1 a b whatever, or closed circle, that is delta. Okay, so of course a closure contains capital A. Now there can be some more closed set that contains capital A. That means A closure is the smallest closed superset of A. So that means whenever I take any closed set C which contains A, then C is subset or equals A closure. So C is a closed set. So I can write A closure to be as and interior of A is union of all closed set contained in A is O. All right. Now suppose so we have defined or we have already discussed about the different types of metric on same topological space. So let us consider that x comma d1 is a topological space and x comma d2 is another metric space. Oh, so for now we have this metric space, a topological space. So when x1, x comma d1, x comma d2 will say to be equivalent with each other. So it is said to open in each other if suppose u is subset of x. So u is open in x comma d1 if and only if u is open x comma d2. So then we say that d1 and d2 are equivalent metric with each other. So when it is possible, this property is possible if and only if there exists rd1 comma rd2 belongs to real numbers larger than 0, such that b with the radius rd1 comma x is inside b of rd2 inside x. Oh no, b d1 not, let's say r1 and r2. It is r1, it is r2, but this is over metric d1, this is over metric d2, and br2, okay, this is over d1, this is over, okay, so this particular property is hold. Then we say that x comma d1 and x comma d2 both are equivalent with each other. So as an example, suppose V be a nonlinear space over R or C. Then we have one norm and two norm. Then both, so these two norms we can define on V with let's say equipped with then D1 is equivalent to D2, where D1 is norm induced metric, one norm induced metric, and this is two norm induced metric. Okay, so both the metric are equivalent to each other. Now, what is a general picture? One can easily check that suppose V is finite dimensional, then it is possible. If we have a finite dimensional vector space and any two norm induced metrics, then both will be equivalent with each other. So what actually this means, that suppose just go to the open ball cases. Suppose in case of, once you consider let's say normal equivalent matrix, there is two normal matrix on R2, you are getting an open disk like this, But once you consider another let's say one norm metric, sorry, this should be one norm metric, it's a mistake, so one norm metric, yes. Once you consider the one norm metric, you are getting such kind of things. So that actually geometrical intuition is the following, that both these two metric will be equivalent, means that if you have any open ball, later will say these are called basic open ball. So any two basic open ball can be deformed into another one. Means suppose we have any basic open ball in one norm metric, that can be deformed in a open disk like this. Similarly, if you have any open disk, you can deform it like this. There is a pictorial representation. Okay, so this is the intuition, that when you say that two metric or metric spaces are equivalent with each other. Now there is also a basic useful metric that we have already defined, that is called standard bounded metric. What is standard bounded metric? Suppose you have a metric x comma t. This is basically a metric induced by another metric. X comma t is a metric space. So once the metric space, then d bar is defined from x cross x to r strictly larger equal to 0, such that d bar of x comma y is equal to minimum of d of x comma y comma 1 is minimum of all these sets, all in d of x comma 1. So then d bar is a metric. So it is easy to check that it is a metric. Like suppose let's say d bar of x comma y, it is 0. So basically that means d of x comma y, it must be 0, right? So that means x equal to y. And conversely also that d bar of x comma x is 0. And also d of x comma y is same as d of y comma x. Then d bar of x comma y is same as d bar of y comma x. But in case of triangle inequality, let us consider d bar of x comma y. Let's take any another small z belongs to capital Z. Then let us take if d of x comma y is what? Is less or equal to d of x comma z plus d of y comma z. So let us consider that d of x comma z plus d of y comma z is less or equal to, or else it is larger or equal to 1. Then d bar of d bar of x comma y is larger or equal to 1, sorry, is less or equal to 1. So that means d bar of x comma y is equal to d of x comma z plus d of y comma z. and that means d bar of x comma y, this equals d bar of x comma z plus d bar of y comma z. Once I'm taking that d bar taking the d values only, but if it is taking at least one, let's say one point is getting 1, let's say d bar of y comma z is 1, so that means what? So d of y comma z d bar of y comma z 1. So of course I can take if it is 1, then yeah, d bar of y comma z is larger equal to 1 always, so I can write it lesser equal to d bar of y comma z as well, as per the value whatever it will take. But the problem will happen that once d of x comma z plus d of y comma z is strictly less than 1. So if it is strictly less than 1, so I must agree that this is strictly less than 1, this is strictly less than 1. So that means d bar of x comma z is must be 1. Sorry, d bar of x comma z must be d of x comma z, and d bar of y comma z, this must be d of y comma z. So that will imply that d bar of x comma y is strictly less than d bar of x comma z plus d bar of y comma z. Okay, alright. So this is a metric we have seen. Now what about the open balls? So how does the open ball look like? So open ball, suppose let delta belongs to real number here, so b delta x is nothing in d bar, of course. Set of all small y belongs to, let's say, x, such that d bar of y comma is strictly less than delta. Okay, so that means minimum of p of x comma y comma 1 is strictly less than delta. It might have not sit in a suitable geometric structure. Let us like in real line, if we consider this one, let's say it is my 0, x to be as 0, so and delta to be as 1, let's say half. So you take any element from here and it's less than half. So of course 0 comma half, this element must come, minus of this must come. Nothing else will come, because if you take any 1, because I mean for any small y it takes the value 1, then it will always go outside, so that point will not be there. But if I take delta to be larger than, or let's say I take 2, so then 0 comma half, so then 0 comma 2 must come, but so then it will be just like let's say 0 and just let's say 1. So like suppose for any small y, so mod of x minus y, it is taking b of x comma y, so mod of x minus y, this must be strictly less than 1. So of course it will take 0, minus 1 and 1 as well. Also it will take on small 1, on 1 as well. Minus 1 as well as sometime minus yeah, just a bit please, we need to take minus 1. Yeah, it will take minus 1 and 1 as well. Okay, so that means it is basically a closed set. So it is a very interesting thing that suppose we take in normal Euclidean metric, once you consider R with a normal Euclidean metric, then minus 1 to 1, this is closed set. But once you take the standard bounded metric, that is Bird, norm of Bird, then this particular closed set is getting as an open set. So minus 1 to 1 is open set. Okay, that's a very beautiful example. So we have introduced a very standard bounded metric. It might be helpful in later cases. So I have just briefly give you an overview of basic topological properties, and in the next lecture onwards we will rigorously start with the topology, concept of topology, and I hope that you will be able to connect those concepts with all these properties with. And I mean, let me just write one thing, that topology is basically a generalized version of metric spaces. So once we'll done with topology, we'll understand that metric space is a special kind of topological spaces. Okay, I have just give a metric space version of the topological properties. In the topological set space as well, we'll define open set, closed set, and done. Okay, so thank you for today.